These galaxies shouldn't exist. Mike Boylan-Kolchin, an astronomer at the University of Texas at Austin, ran the math on 6 of the earliest, most massive galaxies James Webb has photographed, and found they sit right at the absolute limit of what physics allows. So how does a galaxy even get there? To grow this massive this fast, they would have had to turn almost every scrap of surrounding gas into stars, not the roughly 10% galaxies typically manage, but close to all of it. Imagine a factory built to produce 10 cars a year that opens its doors and turns out 1,000, with nobody able to explain how. Not close to broken, at the edge of it. For a while, the reaction inside the field was genuine alarm, the kind of result that makes people quietly check their own math twice before saying anything in public. But how do you even measure something like that with any confidence? Webb doesn't guess distance from a galaxy's color the way older telescopes had to. Its NIR-spec instrument breaks the light apart wavelength by wavelength and reads the redshift directly, closer to matching a fingerprint than making an estimate. Before Webb, the record for most distant confirmed galaxy sat closer to redshift 11, pushing Hubble right to the edge of what its optics could do. Webb didn't nudge that number forward. It blew past it more than once within about 2 years. The clearest single example just cleared its final hurdle. A galaxy called MOM Z14 exists just 280 million years after the Big Bang, the first 2% of cosmic history, confirmed at redshift 14.44, a measure of how much the universe's expansion has stretched its light on the way to us, and therefore how far back in time we're actually looking. The previous record holder, JADES GS Ziyad 14.0, sat at redshift 14.32. Both discoveries arrived within roughly a year of each other, each one pushing the observable boundary a little further back in time. For a while, that claim rested on a single unreviewed paper, the kind of result astronomers treat as provisional until other scientists get a chance to pick it apart. In January 2026, the study finally passed peer review and was published outright, meaning independent experts had scrutinized the methods, the data, and the conclusion and found no reason to reject it. What had been one team's provisional result was now a peer-reviewed finding the field had to take seriously. Rohan Naidu, the MIT astronomer who led the team behind it, put the problem plainly. Webb is showing something that looks nothing like what anyone predicted. And MOMZ14 isn't a single outlier. Peter van Dokkum, a Yale astronomer who worked on similar measurements, has said there appear to be roughly 100 times more bright early galaxies out there than anyone forecast before Webb ever flew. It isn't just one impossible object that slipped through the data, and MOMZ14 itself carries an unexpectedly high ratio of nitrogen to carbon, chemistry suggesting that an earlier generation of stars may already have lived and died before it. Then came a correction, and this is the part that almost never gets told outside the field. When these compact, unusually red objects first started turning up across Webb's deep field images, nobody had a name for them yet. Astronomers just started calling them little red dots, because that's what they looked like on screen, before anyone understood what was actually generating that color and compactness. Catherine Chorowski, a graduate student at the University of Texas working under Stephen Finkelstein, went back through the data in 2024 and found that many of these apparently oversized galaxies owed their brightness to their own black holes. What was actually going on inside them? It turned out their cores were active galactic nuclei, or AGN, black holes devouring enormous amounts of gas. As that infalling material spirals inward, it heats to extreme temperatures and floods the galaxy with light, and from billions of light years away, that glare is hard for Webb to tell apart from the light of the stars themselves. A small galaxy with a hungry black hole at its center can look almost identical to one with 10 times more stars because the telescope measures brightness, and brightness had always been treated as a reliable stand-in for mass. In these cases, the black hole alone was doing the work of billions of suns. Once the little red dots were pulled out of the sample, the case for a crisis seemed to disappear. Finkelstein put it plainly afterward. There is no crisis in the standard cosmological model, at least not from the galaxies. So what's actually true? Are these galaxies really too big, or were astronomers simply fooled by black holes posing as bigger galaxies? And here's where it gets uncomfortable again. Even after every little red dot was removed from the sample, roughly twice as many massive galaxies remained as the standard model expects. Not a handful of stray objects, but a steady, repeating excess, the kind you'd feel in your gut if you were the one staring at the numbers every night. Not enough to break the model outright, enough to bend it. Some of that remaining gap could still come down to ordinary measurement uncertainty, since pinning down a galaxy's mass from billions of light years away is never exact. But Chwarovsky's own explanation points somewhere more interesting. Stars may have simply formed much faster in the early universe. In the denser conditions of that era, less gas could escape during star formation, making the whole process far more efficient than it is today. That's a plausible explanation. It also means astronomers would need to rework part of how they think galaxies form. What if it isn't the galaxies that are wrong, but our sense of how quickly the early universe was capable of changing? Nobody credible is arguing the Big Bang itself is mistaken. What's actually being questioned is something narrower and maybe more interesting. How fast structure could really form out of the early chaos, and whether our models for gas cooling and star formation are missing a piece nobody has identified yet. That's a smaller claim than saying physics is broken. It's not, however, a small claim, and mass isn't even the only place it's happening. In early 2025, Webb photographed a fully formed spiral galaxy from this same early era, its arms already wound into a smooth, rotating disk, the kind of structure that normally takes billions of calm years to build. Thamia Nanayakara, the Swinburne University of Technology astronomer who helped find it, said the galaxy either assembled its mass with unusual precision or formed much of its stellar disk in place without the violent mergers astronomers normally expect for a galaxy that size. A separate team at Cambridge studied more than 250 galaxies from that same early era and found the opposite pattern. Most were chaotic, clumpy systems that had never settled into anything resembling a smooth disk. That contrast doesn't make Big Wheel less strange. It makes it stranger, a single calm exception sitting inside a much messier crowd. Nobody has explained why the same slice of time produced both. Two separate kinds of impossible, found a year apart by different teams using different instruments with nothing in common except how early they both showed up. Whatever built the early universe wasn't just fast. It was fast in ways nobody had thought to prepare for.